Hello friends, let's have a look at problem 1963, minimum number of swaps to make the string balanced. So actually for this problem, you can compare it with problem 921. And essentially the code are the same. However, the returns are different due to the operations here and in problem 941 are different, right? So here we are given a zero index string S of even length. The string consists of exactly half opening brackets and half closing brackets. So here it defines what do we mean by a string is balanced. So here the operation is that we may swap the bracket at any two indices any number of times. So that's the main point of this problem. So we can swap the bracket at any two indices, right? So this basically determines the number of swaps we need, or the minimum number of swaps we need to make a string balanced. So here we can look at example 1. So in this case, right? So you have only this, because these two are actually cancel out because they are balanced. So you have only one pair. So the swap, right? The swap will be only index 1 and index 0. So you get a balanced one. So this gives one operations. However, this is not the case. Now let's look at example 2. So example 2 actually is still not general. So let me do this. So for this one, so we have two, right? These two are not balanced and these two are also not balanced. But because we can swap at any two indices, we can swap indices 0 and 3. So what we get is, so because the middle two are like this, right? If we swap 0 and index 3, so we get this one, right? And this one. So the string is balanced, right? So in this case, we only need one. The reason is that if we have more unbalanced pairs, so because we can swap any two indices, we just need to make one swap, right? For example, here we have two pairs unbalanced. We just need one. But if you only have one, right, you just swap, you need one swap. So here, you see this situation. So you have three unbalanced pairs. So as indicated by problem 1, so this example, you can use one swap to balance two of them. For example, I can balance the middle one. I can put it to be a close one, and right. So we swap this one, and then we remained one pair. So we just need to swap it. So we get this one and this one. So in other words, we need 1 plus 1. So that's 2, right? Actually, this number is nothing but 3 divided by 2. But you take the ceiling, right? So this the ceiling will be 2, or you can compute as 3 plus 1 over 2, right? But now, if for the general case, so this is we just need to compare the unbalanced pairs, and then we just use this. We compute the number, get the number of unbalanced pairs, right? So then we just compute the ceiling, right? And then we return this one, right? So this is the general thought, but because of the restriction of this problem, we have half opening brackets and half closing brackets. So we just need to another way we can track this unbalanced pairs is to track the difference in number of closed and number of open, right? So after you get this one, you just need to compute the the ceiling. This is actually the difference will be the number of unbalanced pairs. So if you have already seen the video for problem 921, actually the first solution, actually we are using a stack explicitly. So we can do the following. So we can use an extra. So this extra is track the unmatched closing bracket, or bracket. So then I also use a stack. The stack will basically track the number of unmatched open ones, but because this they have n over 2 and n over 2 both. So when we do the compute, we just need to compute the unmatched, right? So what we are going to do is for character in S. So if the character is a open bracket, so we are going to put it to the top of the stack, pinned character. Otherwise, so the character is a closed one. So if we can match one with the element in the stack, then we just pop from the stack, right? We don't increment the extra. So in other words, if stack, right, then what we are going to do is stack pop, right? Otherwise, because we have an isolated closed bracket, so we're going to do unmatched or extra incremented by 1. This is like something like this, right? So we have some balanced one, let's see, and then we have a closed one. But in view of the nature of the problem, the string one case of the string will be something like this. These two pairs cancels, then you have an extra one, and then you have an extra one. So this is the one pair, right? You just need one operation. So that's the logic of the problem. So up to now, so after we get this extra will be the unmatched closing bracket. It also equals the unmatched pairs. So we are going to count how many, what's the number of this. If this is an even number, we just divide, return extra divided by 2. If it's odd number, we are going to get the even part divided by 2 and then add an extra 1. So overall, what we want to return is extra plus 1 divided by 2. Right, so let's do a quick run. And it passes all the cases. So now up to this current time, so I would suggest that you compare this code with the code for problem 921. You can see actually they are identical, but the returns are different. So here we return extra plus 1 over 2. But in problem 922, what we return is the extra plus the length of the stack. Because in problem 921, we need to add for each unmatched half parentheses. But here, because we are doing swaps, so for one swap, they can actually balance 2 unmatched pairs. But if you just have one, you just also need one swap. So that's one solution. So here, let me copy this part. So I want to give you another one. So which does not explicitly using so we see implicitly using the stack data structure. So this is actually very very simple, right? So we just have a extra equals 0, and then we have n open equals 0. This is in parallel with problem 922. So then for character in S, if character equals see the open bracket here, then we're going to do n open increment by 1. Otherwise, what we are going to do, so if n open is greater than 0, right? Then you can just do that if we write if n open, right? So we are going to do decrement by 1. Otherwise, so we cannot match this pair, so we are going to do extra increment by 1, right? Again, so we return extra plus 1 and divide by 2, right? Let's do a quick submit. Yeah, it passes all the cases. Actually, you can see from here. So because of the problem nature, so this open actually does not used yet. And another thing is that, so no matter what you do, so if here open is greater than 0, so you are doing open minus 1, right? So in other words, so we fixed an extra and then decrement an open by 1. So overall effect actually is that the increment is the increment by 1, right? So anyway, so it looks like this does not play a role. So in other words, you can further refine the code like this. I'm going to call this one version v2. And then what we do is that we can actually delete this part. So what we want to do, say if an open equals 0, so we can do, right? So we can do the extra by 1, right? So now let's do test. Yeah, it passes all the cases. So here, I guess, yeah, we cannot do this because here we open, and yeah, because it will affect this part. So let's ignore this one for now. So here, actually, we are doing this problem following the exact same thought process as problem 921. But now I want to write a similar code, but it's using slightly different thought process. So I'm going to call it v3. What we want to track actually. Wait. So let's see. I'll see if it's right. Print 1. Let's give 1. Unmatched. I see. So here we also have a self. Let's see. Main swaps. Let's see. Okay, so now we set the correct function signature. So what we want to do actually is we can track the maximum difference between close and open parentheses. So for a valid, parentheses or bracket strings, so the enclose and open, at most, the difference is a -1. Let me give you an example. So let's see. This is an valid one, right? So if you track the enclosed and open, right? So at index 0, so enclosed is 0 and the open is 1, right? And then at index 1, the enclosed is 0 and the open is 2. And at 3, so the enclosed is 1 and the open is 2. And 3, so close is 2, open is 2. If you look at the difference, so I'm going to compute this one. Max enclose minus open. So what you get is 0, right? Also 0. And here also 0, also 0. So for this problem, it means the return would be 0, right? So this is an example. So now if you look at example 1, let's also do the same thing, right? Example 1, let's see, S is given by this one. So let's see, n open and n, not n open, n close and n open, right? So at index 0, n close is 1 and n open is 0, right? And index 2, not at index 1, so n close is 1 and n open is 1. So at index 2, so the n close is 2 and n open is 1. So at index, let's see, 3, right? The n close is 2 and n open is 1. So if you look at their difference, right? So still I'm computing the max n close minus so n open with respect to 0. I will see here. N close minus n open, 0. So this will be 1, and then this will be 0, and then this will be 1, and then this will be 1. So the max is 1. So it means that there's one unmatched pair. So what we are going to return is actually we compute 1 over 2 the seeding. So it's 1, so plus 1 actually over 2. So this is the example 1. So you can also do example 2. So let's do it here. Example 2. So here we have 3 closed one and 3 open ones. So n close, n open, and max n close minus n open and 0. So here at index 0 you have 1 close and 0 open, right? And at index 1 you have 2 close and 0 open. At index 3 you have 3 close and 0 open. At index of let's see, 3 you have 3 close and 1 open. So next index you have 2 open and 2, and the last one you have 3 close and 3 open. So if you compute this one, so you are going to get 1, right, 2, 3, 2, 1, 0. So the max is 3. So if we compute the seeding of this number over 2, so we get this 2. So max equals 3 means that there are 3 unmatched pairs. And then this is computed seeding means this is what we want to return. So now let's write code using this way. So what we want to do is the following. Let's see. I'm going to define a variable like call this, right? And then I compute n open, n close equals 0, 0, right? And then we are going to do the same for loop for character in S. So if character equals this open bracket, so the number of open is incremented by 1. Otherwise, so the number close is incremented by 1. So in between, we always compute the max difference. It will be the max of its previous state, max difference, and then the max of n close minus n open with respect to 0, right? So now after we get this, we can do max diff plus 1, then return the string. So now let's do a quick test. It passes the one example. This is example 1, I guess. Now let's look at the generic case. Yeah, it passes all the cases. So now I would like to do that again. Hopefully this time I do it right. So what I want to do is I copy this part. So I want to mimic the first solution using stack, right? So what I want to do, so here let me call this one v3. Then maximum difference. So then here we are only focusing on the differences of this one. So notice that here, after this if else, I just directly increment this enclose by 1 due to the problem setting. But now actually if we want to write as in problem in the first solution, I can do something like this. So else, so if it's a closing one, if n open is greater than 0, right, then I can do n open decrement by 1. This corresponds to, you know, pop one open bracket from the stack, right? Then otherwise I do this enclose plus 1. So now if you do the test, so it will pass, right? So notice that this 4 lines of code actually it equals this one in effect, right? The reason is that in this if block, so here, so I decrement the n open by 1. So in this case, I didn't modify the enclose. In other words, the difference between enclose and n open is incremented by 1, right? So or you put another way. So you keep n open but increment enclose by 1, right? So this is this if clause. And this else clause, I didn't do change n open, but I incremented enclose by 1. So this effect again makes the difference between enclose and n open incremented by 1. So no matter what, so in this if else block, this 4 lines of code, it corresponds to keep n open fixed and then increment enclose by 1, right? So this is actually the connection of this way of thought. By this way of thought is that if I check this an open one, I directly increment n open. Otherwise, I increment enclose, and then in between, I monitor the maximum difference between enclose and n open. So this is the one way of thought. It's more direct. Another way of thought is using this 4 lines of code, right? So in between, if there are some matching ones, I'm going to match that. So this comes to if n open is greater than 0, I'm going to decrement the n open but keep enclose unchanged. Otherwise, if this is an empty stack or n open is 0, so I'm at a closing one, I'm going to increment the n close by 1, right? So the effect of this 4 lines of code and this 1 line of code are the same, because here we are considering max difference, right? So this is a very subtle point, I would say, but you know, in code actually the effect is are the same, but in thought process they are completely different. So with that said, I hope that you have grasped the idea of this format, right? So overall, I guess that's sufficient for the current problem. And I emphasize again, you can compare this problem with problem 921 to get a genuine understanding about these 2 problems. So with that said, I guess that's about it for the current video. Thank you.